Have you ever wondered what are the causes of queues and waiting lines, or why queues and waiting lines are formed? The reason that we have queues is a temporary mismatch between supply and demand that can be caused by several factors, including mainly by a variation in arrival of customers and variation in providing the service. Unlike products, services, as you know, cannot be completed and finished and stored in, for example, an inventory as it is. Managing a queue. The purpose of managing a queue is to minimize the cost of a queue. We can break down the cost of a queue in two categories. The cost of queue made and caused by the service cost, providing the service, and the cost of a queue that is caused by the waiting time or the waiting cost of a queue. So the total cost of a queue is service cost and waiting cost. You can think of as service cost as also capacity cost. That's increasing, for example, the service level would require increasing the capacity, for example, increasing the number of bartenders or increasing number of servers, depending on what service level or what service or business type of business you are thinking about or considering. The waiting cost, on the other hand, is the cost of waiting in the line, associated with waiting in the line, or the cost of the line itself. It can be tangible or intangible. For example, it can be the cost of not joining a line, that is the loss of opportunity, and or waiting in a line, buying and never coming back again because the customer feel that it's too time consuming. So now we can actually, to manage a queue based on these two types of costs, we can actually visualize these costs by breaking down the cost of waiting and service cost. So in this graph, we have the plot here. The service level is on the x-axis, and the cost of operating the service facility is on the y-axis. The service level on the x-axis is actually the level of service or the capacity, and the cost of operating service is just the cost of the capacity of the service. For example, how much you have to pay the waitress and waiters and the bartenders or operators or whoever and whatever service it is. Having that level of service and facility would require cost. It would actually be costly. So now let's actually plot the cost of queue on this plot. So this is the waiting cost associated with waiting time. As you see here from left to right, as we increase the level of service or increasing the capacity, as you see here, the cost of associated to waiting time is going to decrease. That's because the waiting time is going to decrease. When you have more capacity, when you have a higher level of service, then the waiting time is going to decrease, and that would end up reducing the cost of waiting time. The other cost here is the service cost, which, as you see here, has a direct linear relationship with the service level. So as we increase the service level linearly, it's going to cost us money. So now if we add up these two costs, the cost of waiting time and the cost of service level, we're going to get the cost of queue. This is the cost of queue. And since we want to minimize this, we are looking for a service level that would minimize this cost. So as you see here, this red dot shows the level of service that would make this minimize the cost of waiting cost, the total cost of a queue. So this is the minimum cost of a queue, which is achievable by this optimal level of service. So this is what we are looking for. This is the purpose of a queue management, to find the optimal point of level of service so that it would minimize the cost associated with queues. Let's see an example for queue management. Consider a coffee shop in which its manager would like to minimize the total cost associated with waiting lines. We have this table here that shows the characteristics of this coffee shop. If you look at this column, you can see the number of baristas, 1, 2, 3, and the cost associated with the waiting cost and also the service cost. They have the average time that customer would have to wait in minutes. If you have one baristas, the customer would have to wait an average of 7 minutes. If you have two baristas, the service level is higher, so the service is faster on average. So a customer would have to wait on average of 4 minutes. If you have three baristas, the average waiting time is 3 minutes. Now, based on this information, we want to compute the waiting cost. So the waiting cost, we can use this formula here. The average number of customers multiplied by the average waiting multiplied by the cost wait. So we assume that there are an average of 5 customers waiting in line, and the cost per minute is $10. So that means $50. We multiply it by the number of customers, the average number of waiting time. So that would be 50 multiplied by 7, that's $350. 50 multiplied by 4, that's $200. 50 multiplied by 3, that's $150. Now we want to compute the service cost. So service cost is just going to be the number of baristas multiplied by cost per baristas. Assume that the cost per barista is $60. We have to pay $60 for each barista. So if you hire one barista, it's going to be $60, two baristas $120, and three baristas $180. Now that we have the waiting cost and service cost, we can actually just sum these up. And here we're going to have $410 if you have one baristas, $320 if you have two baristas, and $330 if you have three baristas. So between these, as you see here, the minimum cost is $320, which is for two baristas. So this means that this coffee shop would have to hire two baristas, and at that level, it would minimize their queue cost. Characteristics of queues. Different queues, they have different characteristics. We can actually categorize different queues based on these characteristics. The main basic characteristic that we can consider for queues are the population source. For example, whether we can assume that there is a finite number of the population source for a standing queue. That's where actually the source of customers or people coming from that source to the system. So we can either consider that it's infinite in some cases and finite in many other cases. So the first characteristic is the population source. The second characteristic is the number of servers, which also is known as the number of channels. How many number of channels or servers are in the system. The third characteristic is based on the variation in arrivals of customers and also variation in service. Or the service and arrival patterns, or the distribution of this variation for these two types of variation, the arrival of customers and the service. And the fourth characteristic is the discipline in which the queue would operate. For example, we can have first come, first serve. That means that if you are first in coming to the system, you're going to be the first one who gets served, or first in, first out, or maybe there is another discipline here. So based on these characteristics, these four major characteristics, we can categorize queues. This is a simple queuing system that is illustrated here. what is called as the calling population or the source of population for that the people that coming from, we can, as we learned before, we can consider it to be finite or infinite number of people. And the number of customers are coming from this source that's going to arrive in the system is from this source. And here we have our system. So our system includes those people who are waiting in lines and those people who are getting the service. And then after they are done, they can actually exit the system. So those people who are in the system, some of them, most of them that are waiting, and depending on the number of service level or the number of channels, there are people who are getting served. The first characteristics that we addressed is the population source. It can be infinite source. Not necessarily it literally means that it is infinite, because most of the time, if not all the time, the system that we are considering the source of the population is finite. Even if it's a lot of people or a lot of customers come in, it's considered as finite. It's a number. But in what situation we consider it as infinite? For example, for those situations in which customer would arrive are unrestricted, or the number of potential customers that would come to the system would greatly exceed the system capacity. In this situation, also we can consider the source of the population as infinite. But most often the source of the population is considered as finite, especially for when the case is that the number of potential customers is limited. Channels and phases. A channel is a server or similar to a server in a service system. It is assumed that a channel or a server can only serve and handle and work on one customer at a time. What are phases? A phase is the number of a step or the number of stages in a queuing system. So each step is called a phase. The number of steps are called the number of phases. We're going to see a visual example of this to make it more clear for you. Let's now see common queuing systems based on the characteristic that we have learned so far. Let's start with a single server, single phase. So a single server, single phase has one single server or single channel. There is one server here that can serve only one customer at a time. And also this is only one step or one phase. So this is a single step, single phase. Single server, single phase. An example of this in reality is an ATM, for example. An ATM is just one step. It's one phase. When you are done with it, that's it. You just quit the system. And each ATM or each server can only work with one customer. So as you see here in our queuing system, this is our queuing system. Customers arrive and wait in line. One customer is served at a time with one server and one step or one phase, and then when he or she is done, he's gonna quit the system and there's gonna come to the next customer. Beneath this picture, we see another version of representing a single phase, single server. Customers would arrive from the population source to the system, and they're gonna form a queue here. There is one server and one single phase here that can serve one customer at a time. When the process is done, the person is going to quit and depart the system. Next queuing system is single server, multiple phases. So there are multiple phases in this system. Each of phases have only a single one server. So let's look at our queuing system here. This is our queuing system. These are the people who are waiting in line. And we have two phases here, phase 1 and phase 2. It happens that each phase here has one single server. One server here for phase 1, one single here, server here for phase 2. So when a customer goes, it's his or her turn, it's gonna go to the first phase, and the server is gonna serve him or her, and when he is done, it's gonna go to the next server, and after that, it's going to quit this system and next customer, next person. An example of single server multiple phases are certain restaurants such as Chipotle. In each phase, you do different steps of ordering the food. For example, you get the tray, you go get the salad, you go get the bread, drink, whatever, cashier, and then check out, and that's it. So there are different multiple actually phases or steps here. Another queuing system is a multiple server single phase. So we have one phase but with multiple server. This is our queuing system. These are the people who are waiting to get service. And this is actually just one single phase. One phase. But it actually has multiple server. Server 1, server 2, server 3. All of these servers, they do the same thing. So a person, when it's a turn for each of these person, he or she can go to any of these if available and can actually be served the same service. So when done, he or she doesn't have to move between these servers because the job is already done and he or she can actually quit the system. An example of this is, for example, a type of restaurant like Chick-fil-A. Another queuing system is when you have multiple phase and each phase has multiple servers. So it's multiple server, multiple phase. As you can see here in our queuing system, we have people who are waiting in line. And here we have two phases, phase 1 and phase 2. Each phase has multiple servers that do the same job here at each phase. So when it's someone's turn, this is actually a laundromat. When it's someone's turn, and we have two phases here. We have the washing phase and the drying phase. So when it's someone's turn, he can go to any of these actually server, any of these machines to wash his clothes. And after it's done, he can go to any of these machines to dry them out. So this is an example of multiple server, multiple phase. One characteristic that we mentioned that make different queues distinguish from each other is the pattern for arrivals and the patterns for service. So here we want to talk about the distribution of arrival and distribution of service. One of the most common distribution for arrival patterns is the Poisson distribution that you may remember from a statistics course. In this distribution, we have an arrival rate that we're going to show it by lambda here. So what we want to do is we want to find the probability that X number of customers would arrive in a given time window of time, and how to compute that probability. So as you see here, this is the formula for Poisson distribution that we can use to find that probability. So this is the probability that X number of people would arrive in a given time window is equal to E, the Neperian number, power negative lambda multiplied by lambda power X divided by X factorial. As you see, lambda is one of the parameters here. So for different lambda, we're going to have different probability here. In the graph below, you can see the probability density function for various Poisson distribution, various lambda here. So you can see it for lambda equal to 1, lambda equal to 2, and lambda equal to 4 with different color. So as you can notice, actually, as lambda increases, this distribution looks like bell shape. It becomes similar to normal distribution, although Poisson distribution is actually a discrete distribution. Now let's talk about the distribution of service pattern. The most common service distribution or distribution of service pattern is exponential distribution that you may remember it from statistics. It is also known as negative exponential distribution. So if you want to find a probability, for example, given an average service time, which we show it by mu usually, the exponential distribution gives the probability that the service would exceed time t with the probability of, as shown here, probability of t is equal to e power negative mu multiplied by t. So depending on mu here, we can actually have different probabilities here. In this graph, you can see the plot of probability service time t based on different mu here. So for mu equal to 0.5, mu equal to 1, and mu equal to 2. As you remember, exponential distribution is actually a continuous distribution, and exponential distribution and Poisson distribution actually are related. They are both belong to what is called as Markovian distribution. Now that we learned about different Qs based on different characteristics, such as arrival distribution, service distribution, the number of phases, the number of servers, etc., etc. Now we want to learn how to represent this. One way is to use Kendall's notation, which is a standard method of describing Qs. In Kendall's notation, we have this notation A, B, S, N, and P. A is the arrival probability distribution. So for example, if it's actually a Poisson distribution, we're going to use M, which stands for Markovian distribution, because Poisson distribution is a Markovian distribution. So we're going to use M if it's a Poisson distribution. B stands for the service probability distribution. Again, if it's exponential, we're going to use M, which stands for Markovian again. S stands for the number of servers. Usually, we are done with these three, but sometimes we can actually use also N and P, which stands for more characteristics we can show a given Q with. N stands for the maximum Q length. By default, it assumed to be infinity. If it's not stated, that means that it's infinity. And P stands for the population size. Again, if it's not stated, that means that is infinity. Let's see an example. We want to show this queue with Kendall's notation. So we have one server here. The distribution arrival is Poisson. The distribution of service time is exponential. And we have one server. So using Kendall's notation, the Poisson arrival time would be shown by M because it's Markovian. Exponential service also Markovian. So that would be M, N, and 1. It stands for one server. Here is another example. We want to show this queue with Kendall's notation. So we have 3 lines with Poisson arrival distribution, exponential service time, and one server for each line, as you see here. So there is one server for this line, one server for this line, one server for this line. Try to show this queue with Kendall's notation. So pause for a minute, please, and then try to come up with the notation. So this is, we have Poisson distribution, so that stands for M. m. Exponential distribution is also m, but we have 3 lines here. So this is a little bit different. So we're going to show the 3 lines by 3m because we have 3 arrival. So that's going to be 3 Markovian distribution or 3 Poisson distribution. We have only 1 server, so that's going to be 1m here, or 1 phase, so that's going to be 1m here, and we have 1 server at each line. So that's going to be 3m, m1. Next example, we want to show this queue with Kendall's notation. So we have one line here. The arrivals follow a Poisson distribution. The service time follows an exponential distribution. But we have 3 servers. 1 phase, but 3 servers. How would you show this with Kendall's notation? So please pause, try to come up with the notation, and then come back to see how it is done. All right, so here we have Poisson arrival. So that's m Markovian, exponential service time, that's also Markovian, and we have 3 servers. So that's 3. So for A, B, and S, we're going to have m, m, and 3. Next example, we have Poisson arrivals, exponential service time. We have 3 servers. The maximum queue length is 4 people, and the population is 20. So how would you show this queue with Kendall's notation? Please pause, come up with the notation, and then come back to see how it is done. So we have Poisson arrival, so that's Markovian. Exponential service time, Markovian. The number of servers is 3, so that's MM3. The maximum queue length is 4, and the population is 20. So that's, we have MM, 3, 4, and 20.